You probably have some intuition that there's some significant difference between the potency of different acid and base solutions. It'll make a big difference whether you get lemon juice on you compared to if you get battery acid on you. The way that we'll be quantitative about this in chemistry is called the pH scale. The pH scale tends to range from about 14 down to 0. 14 being something very basic like lye, and 0 being something very acidic like battery acid. It actually is possible to have a negative pH, or a pH greater than 14. For example, sodium hydroxide, which makes up lye, if you get it as concentrated as you can to where it's saturated, that has a pH of about 15. There are different places, for example, the Ibeko volcano in Russia, where you find naturally occurring pHs of less than 0. The Ibeko volcano hot springs have pH as low as negative 1.7. Concentrated hydrochloric acid has a pH of about negative 1.1. And at the Richmond Mine at Iron Mountain, California, the waters have a pH of minus 3.6. Now, the definition of pH, we're not going to just count the number of hydrogen ions directly because they can vary significantly in orders of magnitude. So we're going to use a logarithmic scale to keep track. And we're going to throw in a minus sign just to make it positive. So our pH we're going to define as being the negative log base 10 of the concentration of H plus in the solution. We can make a similar definition for hydroxide, or OH minus. Minus log base 10 of the hydroxide concentration is the POH. And there's a handy relationship tying these two definitions together, which is that the pH plus the POH is equal to 14. Now, a caution here, this is only true for water at room temperature. Frequently, we're working with water at room temperature, aqueous solutions at room temperature, so this is a very handy relationship. We have to keep in mind that it's not always true. Now, just like with our equilibrium constants, the pH is actually given with respect to a reference concentration of 1 molar. Remember, you can't take logarithms of things that have units on them. So we actually, for our pH, surreptitiously divide the concentration by 1 molar. And same thing for our POH definition. Let's say that we want to find the pH and POH for stomach acid, which has a measured hydrogen concentration, or hydronium concentration, of 0.1 molar. And you'll see either H plus or H3O plus. For our purposes, they mean the same thing. Physically, when you have H plus in solution, it lasts a bare fraction of a second before it reacts with H2O molecules to produce H3O plus. But commonly, we'll just write H plus as a bit of a shorthand, as we did in our pH definition. Well, applying that definition here, pH is equal to negative log base 10 of our H plus, or equivalently our hydronium concentration. Now make sure you do log base 10 on your calculators. Don't punch in log base E. That will give you a different number. And we've thrown in this minus sign here to give us a positive value. So we take negative log base 10 of 0.1, and we get 1, because 10 to the negative 1 power would be 0.1. That's what a logarithm base 10 means. As a shortcut for finding the POH, instead of having to use the logarithm again, we can use our relationship that the pH plus the POH sums to 14. So the POH is going to be 14 minus the pH, and 14 minus 1 is 13.